Okay, so in this one, I want to explain the phenomenon of resonance. This is what happens when omega, the frequency of the forcing function, is equal to the natural frequency of the harmonic oscillator. So recall that all of this work that we did was under the auspices of a crucial assumption, namely that omega was not equal to omega naught. Right? Because if omega was equal to omega naught, then this move of going from this line to this line would be illegitimate, because we would be dividing by 0 if omega is equal to omega naught. I hope you can see that. But that doesn't mean that omega couldn't be omega naught. So why don't we ask ourselves and answer the question, what happens if omega is equal to omega naught? So yeah, what happens if omega is equal to omega naught? Well, if we look back at our analysis here, the place where things will go awry is in our guess. So recall, we found the complementary solution here. That's not going to change, okay? But if the omega that we have here is the same as the omega that we have here is the same as the omega naught that we have there, then notice that if we make this guess of a cosine omega t, if we make that as our guess, well, that's going to be an issue. The issue is going to be that the issue with this guess is that this guess is already included in the complementary solution. Remember, omega is equal to omega naught under this discussion. So if you set C2 equal to 0, so that you get rid of that term there, and you make this C1 equal to A, then you get precisely the guess. Yeah, so in other words, this guess can't possibly work. And in fact, it doesn't work because the way that we found the coefficient was would force us to divide by 0, and that's not legit. All right? Okay. So what do? Well, this is where we revise our guess. So, yeah, let me say, if omega equals omega naught, then x sub p will have the form, or maybe I'll say our guess for x sub p. Remember the remedy when you have this this situation, when your guess is already in the complementary solution, you just multiply your guess by t, by the independent variable. So it's going to be a t cosine omega naught t plus bt sine omega naught t. You're going to need both. I'm sorry. You need both now, the cosine and the sine, okay? And it's going to be a lot of work to figure out what this is. Luckily, I'm just going to tell you the answer because you can figure it out if you want to. But basically, you're going to do a lot of work here. Okay? And what you're going to find is that your x of t, your general solution, will look like C1 cosine. So this is the complementary solution, C1 cosine omega t, omega naught t, plus C2 sine omega naught t. All right. Plus what you end up getting here is F naught divided by 2m omega naught times t sine omega t. Okay? This is the solution that you end up getting, the general solution. You should just believe me because it's true. This is the general solution. And the thing that I want to emphasize, okay, is this last term here. Because do you see this crucial t that's happening there? What this is saying is that what we've got in this last term is a sine wave. But because of that t, as t gets larger and larger, the amplitude of this sine wave is getting larger and larger. This number here is just some stupid constant, some positive constant. And it's being multiplied by this t. And as t gets larger and larger, this thing here is going to grow without bound. The amplitude of the oscillation is going to grow without bound. That's called resonance. In other words, when the and I messed up just a little bit. There should be omega naught. When the frequency of the external forcing is the same as the natural frequency of the object, of the harmonic oscillator, then you get this behavior where the amplitude grows without bound. For a picture of it, do I have it up here? Where here? Here's a picture of resonance. Copy image, go back, paste, allow paste. This is a picture of resonance right here. You see the amplitude of the oscillation getting larger and larger and larger as t goes forward, okay? And you can see how this could be very, very destructive, okay? Here's an example of resonance. You know, have you ever seen an opera singer vocalize? They go at a certain frequency, and it causes wine glasses to shatter. I don't know if this is actually real or I just saw this in a Bugs Bunny cartoon, but something like this, I think, could happen. And how it could come about is the following: if you have a wine glass, this is not a wine glass, this is a water bottle, but when you hit it, it makes a certain tone. Okay, I'm sorry if that was shocking and it scared your cats. And if an opera singer sings with that particular frequency, okay, at that particular frequency, it will cause the resonance to occur, and the wine glass will start oscillating, right? And it will oscillate so much eventually with such great amplitude because the opera singer sustains that note. It'll oscillate so much that the glass will shatter and explode everywhere, okay? And your cat will not be safe. Okay. Yeah, that's resonance, okay? That's a resonance for destruction, but there are instances where resonance can be very, very useful. And I mean, it's kind of remarkable, right? That you can get this kind of oscillation like this just by tuning just by tuning yourself to the correct frequency. You can get this kind of phenomenon to happen, okay? That's resonance, okay? We'll talk a lot more about this because in the next set of videos, I want to do an example where we really understand all of these ideas in the context of a water tower problem, okay? We're going to study a water tower problem, and we're going to see the phenomenon of resonance coming out quite naturally. Okay, see you in the next ones.